Hello there. Recall in a previous video that we were interested in finding for some Cartesian equation, let's call it f, that has some boundary points of interest, say A and B. And we were interested in finding the length of this curve, right? So we were able to find that the arc length formula was equal to the integral from A to B of the square root of 1 plus the derivative of y with respect to x, the quantity squared, times the differential of x. So in this video, we're going to extend this discussion to the discussion of how to find the arc length of polar curves. In particular, we're going to be focusing on the curve that I've used in some other videos, namely r is equal to the sine of 3 theta, and pretty much figuring out how we can find the length of this particular petal, or 3 petals rather, using polar coordinate representations for this formula. Alright, so we're going to begin by focusing on this particular polar curve, and keep in mind that theta ranges from 0 to pi for full traversion of one revolution of each of these petals, right? So we're going to begin writing our arc length formula in Cartesian form in a very equivalent way, but probably not comfortable to some readers, right? So what we can do for this relationship, 1 plus dy over dx, the quantity squared, dx, is we can split up this differential dx as follows. We can represent this as 1 plus dy over dx squared times dx, the quantity squared. And we can distribute the square differential inside, and we get another alternative representation for the arc length of Cartesian terms, right? Such as the square root of these two differentials, which of course reflect the Pythagorean theorem, which pretty much lies in the main derivation of where this formula comes from, right? All right, so we're going to come back to this formula a little bit later, right? So now we're focusing on some r is equal to some function of theta, right? So of course we're going to represent dr d theta as simply just phi prime theta, right? So if we want to convert between polar and Cartesian form, we know that x is going to be r cosine theta, y is equal to r sine theta, right? So of course we have expressions for dy d theta and dx d theta. So dy d theta is going to be equal to phi prime theta times sine of theta plus phi of theta cosine of theta, and then we have dx d theta is equal to phi prime of theta cosine theta minus phi of theta sine theta, right? So that's our equivalent differential system. All right, so the next thing I'm going to do is I'm going to square each of these expressions. So what is that going to give me? So let's focus on dx d theta first. So dx d theta to quantity squared is going to be equal to, so I'm just going to abbreviate this shorthand as phi prime cosine theta minus phi sine theta squared. So just using some quick expansions here, we just have phi prime squared times cosine squared theta minus 2 phi prime sine theta cosine theta plus phi squared sine squared theta. Similarly, dy d theta squared is going to be equal to phi prime sine theta plus phi cosine theta, the quantity squared. So doing some quick distributions, we have phi prime the quantity squared, sine squared theta, plus 2 phi prime sine theta cosine theta, plus phi squared cosine squared theta. So now what I'm going to do is I'm going to take these expressions for dx d theta, dy d theta squared, and then I'm going to add them together, right? So what is that going to give us? So dx d theta squared plus dy d theta squared is equal to. So it's very obvious when we add these two together, this term right here and this term right here are going to cancel, since they're the same thing, just opposite signs for all values of theta, right? For these terms here, they are the same thing except one is sine squared, the other is cosine squared. Same story as here. So we know sine squared plus cosine squared is equal to 1 for all values of theta. So we're just going to have phi prime squared plus phi squared. Now isn't that a beautiful simplification, right? So what do we have here? So let's write phi prime and phi in their more classical representation. So we have dx d theta, the quantity squared, plus dy d theta, the quantity squared, is equal to dr d theta, the quantity squared, plus r squared. And now what I'm going to do is I'm going to multiply both sides by d theta squared. So I'm going to have dx squared plus dy squared is equal to dr squared plus r squared d theta to the quantity squared. And let's see here. Actually, what is a better way of doing this? Oh, so what we can do actually is rewrite this as dr d theta, the quantity squared plus r squared, and just write this d theta squared on the outside. Yeah, that's a lot better. Right, and you'll see why we prefer this in just a moment. All right, so let's go back to our Cartesian representation for our curve. So the arc length is going to be equal to the integral from x is equal to a to x is equal to b of the square root of the squared differential of x plus the squared differential of y, right? And let's just assume that when x is equal to a, theta is equal to alpha, and when x is equal to b, theta is equal to beta. And you can do some justifications here on your own if you wish to sort of see why we can sort of make this assumption. So if that is the case, then we're just going to replace dx squared plus dy squared with this expression. So we're going to have the arc length is going to be equal to the integral from alpha to beta of the square root of dr d theta to the quantity squared plus r squared all times d theta to the quantity squared, right? And the square root of d theta squared is going to just be the absolute value of d theta, which we can assume to be positive without loss of generality. So we have our beautiful polar curve representation, the integral from alpha to beta of the square root of r squared plus dr d theta to the quantity squared times d theta. And this is our polar representation for the arc length of some curve. So let's go back to our 3 rows petal, namely r is equal to the sine of 3 theta, for theta belongs to the interval 0 to pi, and let's see if we can try and find the arc length of this curve, right? All right, so by symmetry, we know that the arc length of this from 0 to pi of this curve, right, the square root of dr d theta squared plus r squared d theta is just going to be equal to 3 times the integral from 0 to pi over 3 of the square root of dr d theta squared plus r squared d theta for this particular function r, right? So we're assuming that in this transformation. So dr d theta, what is that? So dr d theta is going to be equal to 3 times the cosine of 3 theta, and then we're going to be squaring that, right? So this is just going to be equal to 3 times the integral from 0 to pi over 3 times the square root of 9 cosine squareds of 3 theta, and then plus then we're going to square this r thing, so that's going to give us sine squared of 3 theta. And then we have d theta here. All right, so what is this? So we have 9 cosine squareds and 1 sine squared. So we can sort of break that up into 8 cosine squareds and 1 sine squared. So we have 8 cosine squared plus sine squared plus cosine squared, which is 1, right? So we can write this as 3 times the integral from 0 to pi over 3 times the square root of 1 plus 8 cosine squareds of 3 theta d theta. And then we can perform substitution if we want to, right? So we can, let's say, u be equal to 3 theta, and that's going to change our bounds for sure, and that's going to change this, right? That's probably the first step you want if you actually want to try and find this integral, right? So the arc length is going to be equal to 3 times the integral from 0 to pi, in that case, and then we're going to have, this is going to be 1/3 times the square root of 1 plus 8 times the cosine squared of u du, right? And of course this 3 and that 1/3 will cancel, so the arc length of the 3 petals is going to be characterized by the integral from 0 to pi of the square root of 1 plus 8 cosine squared. I can call this x since it's a dummy variable, right? And this is a very simple representation. Now, if you want to approximate this using rectangles or Simpson's method, you can find that this integral is approximately equal to 2.227, right? Approximately, right? But what if you're not satisfied with this? So the question will become, okay, well, how do we deal with this? How do we deal with this analytically? So is it possible to get a closed, nice form for this particular thing? Well, in this case, not very easily, right? All right, so what I'm going to do is I'm just going to shift this integral in terms of sine squared to write it in another way. So I can rewrite this integral as L is equal to the integral from 0 to pi of the square root of 9 minus 8 sine squareds of x dx. And I can, of course, write this as 3 times the integral from 0 to pi of the square root of 1 minus 8/9 sine squared of x dx. And if you're familiar with special functions, then this little integral here is known as an elliptic integral. And this is where sort of a discussion of non-elementary functions usually begins, right? And what do I mean by non-elementary? Well, I mean that you cannot express this antiderivative, at least the antiderivative of this function, in terms of sine, cosine, exponentials, logarithms, polynomials, and a finite linear combination of these functions, right? It's impossible, right? Now, how do you prove that? That's another discussion for another day, right? But this particular type of integral, where we have something like the square root of 1 minus k sine squared of x dx, where we have stuff like this, where we have from, say, the integral from 0 to some angle phi, this is what we call an elliptic integral, which we're going to spend a couple videos on soon after this video. So hang tight and we'll discuss what an elliptic integral is and why do we actually call this integral an elliptic integral, right? Like, how do ellipses sort of fit into this discussion? Because we weren't finding the area or anything about an ellipse, we were looking for the petals of this rose, right? So we'll also answer that question once we get into that discussion, right? But if you're looking for an analytical solution in terms of those other basic functions, in this case you cannot do it. So you would have to use some approximations to show that this is approximately equal to 2.227. So that's the approximation to the arc length of our, oh, where'd he go? Of our 3-petal rose. Anyway, that's just a basic overview of how to find arc lengths in polar curves. In this case, you can't find the closed form in terms of elementaries, but there are some special cases for which you can. The equation of a circle proof, right? You can do that as an exercise. So prove that r is equal to, say, 5. So prove that the arc length from 0 to 2 pi, right? So prove that the arc length of that is going to be 2 pi r, right? That's just an exercise for you to sort of exercise your skills and understanding of this concept. Anyway, that's just a basic introduction to arc length in polar form. Hope you enjoyed.